Okay, next order of business. I did not go through the syllabus last class, and I don't intend on going through it, every little detail about it. But there was something in the class files that I wanted to point out to you. And I thought about this after I made up your quiz for today. And I was like, well, maybe this isn't going to be fair. So under class files here, there's this folder that says formula sheets. And all of these, there's 4 different files here. You're allowed to print those out and use those on any assignment that I give you, whether it be a quiz or a test. Now, a lot of these we don't need right now, but that first one there is just the formulas from the back of your book. So just a real quick show of hands, how many of you have those formulas with you? Who does not? Oh, okay. So because of that, I'm gonna postpone the first quiz, all right? But what I'm gonna do is I'm gonna hand you out the quiz, and this is what I would have expected you to be able to do today, all right? And you just work it on your own for your own. It's not bonus points or anything like that. It's just so you have an idea of what I would have expected you to do. But I also would have wanted you to have this with you, okay? So from here on out, every day, make sure you have the formula sheets with you, okay? Yes? You cannot add on to them. Now, there might be a time where I tell you, hey, this formula is not on your formula sheets, so let's go ahead and put it on there, and I'll let you know. And then everyone can do it. But the idea is that at the test, everyone has to have the same thing so that it's fair. Okay? All right, so here's what would have been quiz 1. And you can just take a look at it and then put it away. We're not going to go through it. I think I might be short one there. Got an extra one there. So it's a good opportunity for you to just kind of reflect, and say, how would I have done on this? And the instructions at the top, I'm coming. The instructions at the top say no calculators are allowed. So you would not have been able to use your calculators on this. There you go. So I would have expected that you can determine some inverse trig functions, find the exact values, and then doing some derivatives using the stuff we talked about last class with inverse trig functions. Chain rules, some product rule in there. So, okay. I'll give you the answers to these, just not right now. Any questions on that? Formula sheets? We're okay with that? You'll notice on your formula sheets there's no unit circle on here. So like if you have like that favorite unit circle that you've been using since pre-cal, like you're not allowed to use that on the test. So just get used to that idea. Again, it's just everyone's going to be level playing field. All right. Any questions? Any questions over the homework problems? No? Okay. Sure. Wait, is this my book? Let me get that out of here. Okay, so this is where we kind of start to get into Cal 2, all right? And I mean, not to say what we did last time isn't, but now we really start to focus on what's the main idea of Calculus 2. And I like to start this out by doing a quick review of the main topics from Cal 1. All right, so if we had to put Cal 1 kind of in a nutshell, who wants to tell me what Cal 1 was about?
A lot of derivatives.
Derivatives, okay.
Finding the tangent line of a curve.
Okay, so tangent lines.
Limits.
Limits. I heard antiderivatives.
Yeah, integral.
So do you feel like you did a lot of that in Cal 1? Like
Not
what
all
what
like
percent
that.
what percent would you say you did?
Probably 10%.
10%? Yeah, so I'm hoping it's like 10% because it should have been a little bit of overlap into this course. And we're going to start today, and a lot of you, this is going to be familiar. I know for students who already had me, like I'm going to be basically repeating a lecture I've already done, okay? So there's some antiderivatives in here, but I'm just going to kind of circle it because that's going to be kind of different for everyone. Okay, I agree. Everything you've put there, derivatives, tangent lines, you needed to take derivative, do that. Limits actually came first, right? The limit was first, and then from the limit you came up with the idea of the derivative. What else? Implicit differentiation. So that was important. We actually used that last class.
Optimization.
Oh, your favorite. Optimization.
Related rates.
Oh, your other favorite one. Related rates.
Substitution.
What's that?
U substitution.
Okay, so U substitution would have fallen into here. Who said that? Okay, so U substitution is in there. So integrals would be with antiderivatives. Okay. Yeah. Sketching curves, right? I think that kind of summarizes what you did. How about this one?
L'Hopital's rule.
Yeah, L'Hopital's rule. Now this we need a show of hands on. Who did not learn L'Hopital's rule? Everyone learned L'Hopital's rule? That's never happened. Okay, so all right, so we are going to use L'Hopital's rule. And if you're not familiar with it, because I know there's some Cal 1 classes they don't cover it, so if you did not learn L'Hopital's rule and we get to a point in this class where I'm like, oh, we're just going to use L'Hopital's rule and you have no idea what's going on, like that's when you need to come talk to me, all right? Make sure you're clear on that. L'Hopital's rule is a way that we can do limits a lot easier using derivatives to do limits. Yeah, I think I'm happy with that. Mean value theorem. So the mean value theorem's in there. That's a super important theorem. We actually aren't going to use it too much. Now we're not going to use it here too much. But the mean value theorem was in there. Okay. Now geometrically speaking, the main idea of Cal 1, and no one has optimization would kind of be there, is we want to be able to look at a graph. We want to be able to find, the peaks and the valleys, right? The highest and lowest points, which is connected to the tangent line. We have this idea of increasing, decreasing functions, concave up, concave down, right? So a lot of what we did in Cal 1 was kind of analyzing the shape of a graph, and talking about that tangent line, how we can use it to find those peaks and valleys. So in Cal 2, what we're going to do a lot, but we're going to start out in Cal 2, at least in this class, we're going to start out with antiderivatives. So we're going to start and we're going to spend several weeks making sure that we are comfortable finding antiderivatives of functions. And if you don't know what antiderivatives are, I'm going to act like you don't know, and that's where I'm going to start today. But we will spend, where's my calendar? There it is. We will spend a good, well, it's going to take us all the way out to February 25th. Okay? Now we will have an exam somewhere in between there, but we're going to spend the rest of this month and most of February making sure that we can find antiderivatives. Now when it comes to antiderivatives, as you'll see, it's a lot harder than derivatives. With derivatives, there's only a couple of rules, right? There's power rule, there's product rule, quotient rule, chain rule, and that's pretty much it. If you can do those rules, like in theory, if someone gives you a function, you should be able to differentiate it. Now you might need implicit differentiation or something like that, but the rules are still just the rules. with antiderivatives, nothing is as clean as that. There's no like rules, it's more what we call techniques. And there are things we try to do to go backwards. That's what antiderivatives is. So it's going to take us weeks to get comfortable with that, and that's these techniques that we learn. There's going to be 5 of them, and they get progressively more difficult. And the last one is just, we wind up doing problems that take us, I'll do 2 problems all class. Like it'll take us all class to do two problems. That's it. So they're long, they're tedious, but that's the nature of the beast. So we'll get through antiderivatives. After we get through antiderivatives, what we're going to do is we're going to do applications. So when it comes to applications, now we start saying, what can we do now that we can find antiderivatives? Now that we can go backwards, what do they mean? What are they useful for? And the applications we start out with is we go back to your function, and you say, okay, if we want, we can take this function, we can look below it, and we can try and calculate the exact area underneath that curve. Right? And that's the antiderivative will allow us to do that. And you may have done that in Cal 1. Again, like in my Cal 1, we did that, but it's just like you're just tipping your toes in Cal 1. You're just barely getting your feet wet there. Right? We will be looking at complicated functions trying to figure out what's the area underneath it. Then we'll do like 2 functions, figure out where they intersect, and then find the area between those 2. And then we'll do something like, all right, take this, we can find its area, take that region, and like imagine wrapping it around the x-axis, like 3-dimensionally, wrapping it around the x-axis and creating this solid object out of it. Can you visualize that? I'll have plenty of visualization for us, but can you, I mean, it's something, some people are very visual, some aren't. So we are going to do that. We're going to imagine wrapping this around the x-axis 3-dimensionally and then trying to find the volume of that solid. Okay? And then we'll do things like, all right, we'll go back to the curve and we'll say, all right, take that curve again. Instead of finding the area, how long is that curve? Like if you took that curve off the page and straightened it out like it was a string or something and straightened it out, like how long is that? So it'd be like if you were walking along this path, it would be the distance you would travel. That's called arc length, and we'll find that. That's actually, it turns out that finding the area and the volume and stuff, and these areas and volumes is actually easier than finding how long that is. This is usually a much more difficult computation. And then we'll go back and we'll wrap this thing around again, and we'll say, instead of talking about volume, we'll talk about surface area. Can you find the surface area? So those are some of those are like the most common applications. And then we'll have to pick, there's one section in the book where we can get very specific, like do we want to talk about finding, like this is all connected to finding the center of mass of something. We can talk about hydrostatic pressure, we can talk about work. I mean, there's different things, but you have to remember this class is math. It's a math class, so we will kind of talk a little bit about specific applications to maybe engineering or something, but this is not an engineering class. So the idea is that when you get to the engineering class, you've got the math background, and then they show you how to use that math in that class. So we'll just dabble into it a little bit. And okay, so we get through with all that, and then that's going to be about 2/3 of the class. That'll take us through about the end of March. And then we get into the final chapter, which is called series. And this is usually the big, difficult one. And the reason it's difficult for most students is because, I mean, there's a lot of students, not a lot, but there's some students that come out of high school and they've seen some Cal 1 and Cal 2. They've seen some of this stuff. But usually series is brand new for everyone. Like it's a new concept. And we will get into this, we will spend from March, all of April and part of May doing series. And after we finish this, if we finish, we will finish chapter 8. We'll get into chapter 9. But to me, chapter 9 is, if we get to it, great. If we don't, I think it's something that, if you can do chapter 8, then you could probably go read chapter 9 on your own and learn it. Like, does that make sense? Like, if you can get through series, like you have mathematically matured to the point where you can absorb chapter 9 without much direction. All right? So this is going to be a long journey. All right? I love teaching this class. It's one of my favorite ones because this is going to be a journey. Like, most students are going to be challenged in this class at some point. And, you know, everyone's different. So we'll find out where you are. And, yeah. So maybe I should talk about series just to kind of give you an idea. I'll give you one small little glimpse of what series, how series not work, but like where they're used. So if you get on your calculator, if someone has their calculator right now, type in e squared on your calculator and just give me what decimal it gives you. What is that?
7.389.
So it's approximately 7.389?
Yes, sir.
Okay, and it probably goes on a little more, but we'll stop there. Okay, so the question is, you know, well, let's do one more. Let's do sine of 2. And let's be in radian mode. So what does your calculator do there?
909,
What is it?
0.909.
0.909. All right, so the question is, what did your calculator do in order to get those two numerical answers? Right? So calculator can only do what? What are the only things a calculator can do, or a computer can do? And what are the only arithmetic operations it knows how to do? Ones and zeros are like the language of it, right? It only knows on and off. But in terms of arithmetic, a calculator or computer can do addition, subtraction, right? Multiplication, division. That's pretty much it. Everything else is like some combination of those. So what arithmetic did your calculator do in order to get those two answers? Does your calculator know that the sine function is like based off a right triangle, or does it know that there's like a unit circle involved? Does it have any idea? No, this is just some arithmetic operation. So what did it do? Well, I can tell you that what it did was for e to the x, or e squared, it's using a built-in function that's pre-programmed into your calculator that says that e to the x is exactly 1 plus x squared over 2 plus x cubed over 2 times 3 plus x to the 4th over 2 times 3 times 4 plus x to the 5th over 2 times 3 times 4 times 5 plus ... That goes on forever. And this is what we call an infinite power series. Right, this is a series of things, a series of terms, and it's infinite. And it's called a power series because every single term of the series is a power of x. Do you all agree these are all powers of x? So when you typed in e squared into your calculator did this. 1 plus 2 squared, which is 4 over 2, plus 2 cubed, which is 8 over 2 times 3, which is 6, plus, where are we at, 16 over 24, plus, okay? And it went out, and there's something pre-programmed into your calculator that told it to stop somewhere, okay? So e to the x actually goes forever, but your calculator can't go forever, right? So it stops, and then it spits that answer out. So if you, I'm not asking you to do it now, but if you got on your calculator and you typed in 1 plus 2 plus 2, right, that's 2, plus whatever this is, plus, you would get pretty close to 7.389. And the further out you go, the more precise your answer is. That's what your calculator did. So the question is, how do we figure out that e to the x is this, right? How did we figure that out? And that's where series come into play. And it turns out that if you give me any function, there is a way to turn it into a series, all right? There is a power series for, I'm not going to say every function. There's some restrictions here. But generally speaking, if you have a function, we will be able to find a power series for it, all right? There's like a process to do it. And so when you're dealing with computer science, right, anytime you're programming a computer, you're dealing with functions, you're most likely going to be working with their power series, not the function, like the function in its other form. All right? Let me show you sine. Y'all want to know what sine is, right? Of course. Okay. I'll show you what sine is right here. So sine of x, just give me a moment to think. X minus x cubed over 2 times 3 plus x to the 5th over 2 times 3 times 4 times 5 plus, minus x to the 7th over 2 times 3 times 4 times 5 times 6 times 7 plus what's next? X to the 9th over, there's another way I can write that, 9 factorial, and I'll talk about that later, but there's a shorter way to write this. We use 9 with an exclamation point. Don't worry about it. Okay, and that goes on forever also, okay? But notice the pattern switches, like positive, negative, positive, negative, positive, negative. Okay, so if you were to plug 2 in here, 2 here, 2 here, 2 here, calculate it, you're going to get something close to 0.909, all right? I'm going to do one more. I didn't put cosine up there, right? But I'm going to put cosine here. Cosine x is 1 minus x squared over 2 plus x to the 4th over 2 times 3 times 4 minus, what do you think? X to the 6th over 2 times 3 times 4 times 5 times 6. That's terrible, 5. You get the idea, okay? X to the 8th. All right. Now, y'all ready to see something blow your mind? This will blow your mind. No, not this. I'll tell you when it's going to blow your mind. Do you remember in pre-cal we said sine is an odd function? It's because its power series contains nothing but odd powers of x. Cosine is an even function, and all the powers of x in its power series are even. If you had a function that had a mixture of odd and even, it's neither odd nor even, right? And e to the x is not an odd function, it's not an even function, okay? Now, you ready for the mind-blowing part? What's the derivative of e to the x? Itself, right? So watch this. If I take the derivative of this, right? Let's just take derivative of this, right? Okay, what's the derivative of 1? 0. Okay, what's the derivative of x? 1. Okay, plus. What's the derivative of x squared over 2? So the 2 would come out, cancel, right, and you'd be left with just what? Okay, let's do the next one. The 3 would come out, cancel with this 3, and you'd be left with what? X squared over 2. Plus, the 4 would come out, cancel, and you'd be left with x cubed over 2 times 3. We'll do one more. 5 comes out, cancels, you get x to the 4th over 2 times 3 times 4. Now, what is this function? It's that function. They're identical, right? They're identical. It is its own derivative, right? What's the derivative of sine? What's the derivative of x? What's the derivative of this? Right? What's the derivative of this?
X to the 4th.
You see it? Okay, that's pretty cool, right? What's derivative of cosine? Negative sine. Okay, so let's see. Derivative of that's 0. Derivative of this? Negative x. It's that, but negative. Okay, what's the derivative of this? 4 comes out, x cubed over 2 times 3. Right? But negative. See? So this to here, the derivative of this is not quite this. It's just this with the sign changed. So, yeah.
You should show us that in Cal 1. Get an idea.
Yeah, well, we wait, I guess, till Cal 2. So we have big things ahead of us. And like I said, we're going to spend a full month or more trying to figure out how to find the antiderivative of things, right? Okay, that's why I said we're going to have these techniques and we're going to try. It's going to be challenging. But in the big picture of things, in the real world, if you were to just be presented with some function that you have to find the antiderivative of, chances that you could actually find that antiderivative are essentially zero. Okay? I mean, if you just, like, the way I like to think about it is if you had like a big pot full of all the functions that are out there that have antiderivatives, and you reach in there and you grab a function, the chance that you can find the antiderivative is pretty much zero. Because the 5 techniques we're going to learn they break down. It's not like differentiation where there's just a process. So how do we deal with that? Well, what we do is we convert the functions into their power series. And then you can find derivatives and antiderivatives easily, very easily. Wasn't it easy to differentiate that? It's going to be just as easy to define the antiderivative. So as long as we can convert a very nasty function into its power series, we are in business. Okay? So series are super important.
When do we apply that?
Pardon?
When do we apply
Well, that's what I was just trying to explain. In the real world, you're presented with functions that are not nice. Like most of the problems that are in our book that we're going to do for homework for antiderivatives are specially made so that you can actually get the answer. Okay? But in the real world, you can't. So what you need to do is convert it to its power series. And then all the differentiation and antiderivative stuff is easy at that point. Okay? Does that? So.
With that, I was asking, are we going to be able to attempt that in the scope of this course? Or
Yeah.
is it more Calfreedom?
Yeah. On your final, I'll give you a function that you cannot integrate with any technique, and I'll ask you to find the area underneath it. Yeah. Which later on could mean something else, like the total work done or something.
Yeah, I was confused when you're.
Yeah.
Were you saying that it's beyond the scope of this course or within the scope of this course?
Pretty much everything I put up here is we're going to talk about again. Yeah. And I have one more thing on series. We were talking about this, right? Omar and I were talking about this today. Just something that you can look forward to. This equation you may or may not have ever seen before. You all seen that? It's argued to be the most beautiful equation in math. And the reason it's argued to be that is because it contains all of the really good numbers in math. And it's actually true. It's a true statement there. So let me discuss a little bit why these are important numbers. Well, first of all, let's start with 0. Why is 0 so important? Well, it's what we call the additive identity. It's the number in our number system that when you add it to something, it doesn't change it. And as trivial as that sounds, you know, like x plus 0 is still x, right? As trivial as that sounds, not all sets of numbers have additive identities. So our number system has one. We also have number 1, which is another identity. What identity is that? Not the additive identity. Multiplicative identity. So if you take 1, x times anything, or x times 1 will still give you x, right? So with addition, with 0, nothing changes. Multiplication with 1, nothing changes. So you have both an additive identity and a multiplicative identity, right? So those are super important numbers in our number system. What about pi? Why is pi so important? Well, that's the ratio. Pi, by definition, is always the circumference of a circle divided by its diameter. That's the definition of pi, circumference over diameter. So that's an important number, right? We've used it quite a bit. What about e? Why is e so important? Does anyone know why e is so frickin' important to us? The graph of it, right? The way e to the x looks. But doesn't 2 to the x look the same, kind of? What is it about e to e that is so important? Well, I kind of already showed you. E to the x, right? That function, when you differentiate it, what do you get? Itself. And it's the only function that does that. Like if you took 2 to the x, well, let's do it this way. E to the x, if I take its derivative, what is it? Okay, but if I take 2 to the x, take its derivative, I get 2 to the x, but then I have to multiply it times natural log of 2. That's something from Cal 1. And so this right here makes it not quite the same as it originally was. E to e is the base that you need to have on your exponential function so that when you take its derivative, it is itself. And it's the only number that works. And so that's a very important number, right? And then the last one is I. So I, why is that important? Well, what's the definition of I? It's the imaginary unit. It's what you get when you take the square root of -1. So all of these very important numbers, all tightly packed into a nice equation. And I'll prove to you that that's true. Okay, we'll prove this.
But what is that equation's purpose?
It's not, there's not a purposeful equation at all.
Okay.
It's just, that's why people just say it's just the most beautiful equation, because it just looks, it just brings these great numbers together. In all practicality, all this is really saying is that this is equal to -1. Would you agree that's all that's saying?
Yes, sir.
Okay, and then, you know, later on, if you're a math major, you'll take a course called complex variables, where you're like, yeah, well, duh, this is -1, big deal, you know, and this equation's like, yeah, big deal. But people like it. They call it the most beautiful equation in math. So I'll prove to you, I'm going to prove this to you. That's what we'll prove. And we'll have to use power series to do it. All right, I'm done talking about it. Let's get down to business. Y'all ready? Okay, let's do it. All right, now the fun's just begun. All right, so we're going to start out with antiderivatives. Antiderivatives, where are they? So, quick show of hands, who did not cover antiderivatives at all in Cal 1? No antiderivatives? No? Okay. All right, so I'm still going to treat it as if y'all have not seen it, or maybe the way you saw it was a little different than the way I want to present it, so still pay attention. Remember, these notes are online, so don't worry about sitting there copying all this down. You can get to them later. So this is just definition here. A function capital F is called an antiderivative of little f on some interval I if the derivative of capital F is little f for all x and I. Okay. Math definitions are always so much fun, aren't they? So all this is saying is that if we have some function, and we'll start out very, very simple. Say we take that nice linear function. To say that another function, capital F, is an antiderivative of this, okay, capital F, to say it's an antiderivative of this means that when I take the derivative of this, I need to get that. So what could I use here? The derivative of what is 2x? X squared, yes? That is an antiderivative.
Plus C.
Okay, so you have to act like you don't know that yet. Okay? Or otherwise, I just start where you don't know.
So it's just like reversing the process.
It's reversing the process. So do you all agree that this is an antiderivative? Mm-hmm. But it's not the only one. So someone else could come in and say x squared plus 3, right? And that would still qualify, because if I take the derivative of that, you'd still get 2x here. The derivative of a constant is 0. So that would work, right? Would this work? Would that work? That won't work, because then you'd get 6x, right? And that wouldn't qualify. Okay? I could do x squared and subtract a number, right? So as long as I have the x squared there, I'm going to get the 2x when I take the derivative. If I tack on any constant I want on the end, no matter what it is, when I take its derivative, it'll go to 0. So these are all specific examples of antiderivatives, but what we'd like to do is write out what's called the general antiderivative. The general form of an antiderivative of that function 2x would be x squared plus any constant. And just keep in mind that this constant, I'm representing this constant could be a positive number or a negative number. So the plus really isn't that important, because this could be plus 2 or it could be plus negative 2, right? So this is our answer. Now, what's important to notice about this is that there are an infinite number of answers, aren't there? So if someone gives you a function, asks you to find the general antiderivative, you're finding an infinite number of functions, but they all have something in common, right? These would all be parabolas, wouldn't they? They would all open upward, and this C would just shift them up and down. So what we say is that this right here creates a family of functions. This is a family of functions. I mean, they're related in some way, right? They're not exactly the same, but they are similar. And I think you can see it if I illustrate it with a picture. This is really annoying. I'm just gonna, I don't know where I want to put, I can't turn this thing around, my mouse keeps sliding. Okay, maybe I'll try that. Okay, yeah. So what I have graphed up here is the red function is 2x, right? Red function is 2x. And the blue function you see here is a specific antiderivative. It's x squared minus 8, all right? So it's just that parabola moved down 8. But if we look at the family, we're talking about all of these guys in here, right? All these parabolas. Would you agree?
Yeah.
Okay. And what they all have in common, let me get a little less. What they all have in common is that when you go to some value x, let's say I go to some value x into here, right? So let's say I pick one of these and I go to the value x, I go, here I am on the function, right? And if I ask you what's the slope of the tangent line there, I have to use its derivative to find the slope of the tangent line, which is 2x, and that would give me the slope there. But that slope will be identical on all of the members of the family at that point. That's what it's saying. So even though these are moved up and down, they all have in common a same slope of a tangent line if you look up and down. Make sense? Okay. So students will forget sometimes to put plus c at the end. And some professors are really hardcore about that. If you forget plus c, then you're missing an infinite number of answers, right? So it's wrong completely. I take off, but I don't take off like completely. I'll be kind of easy on you in the beginning if you forget c, but I will count it wrong, part of it wrong, and then as we progress through the semester, I'll take off more if you keep forgetting it. All right? Okay, so that's the general idea, is that we have a family of functions. Now, how did we find the antiderivative of 2x? How did we come up with x squared?
N plus 1.
Yeah, but you just knew it, right? Like you knew that the derivative of x squared would give you 2x. And there's probably a lot of things from Cal 1 that you could do that with, because you know what the derivative of it is. Do y'all agree? So let's see if we can't kind of come up with a list right now of things that we are comfortable with finding the antiderivatives of. So let me just put a function here. And then over here, next to it, I'm going to put its antiderivative. Who wants to volunteer the first one? Whatever you want. Some function you can think of from Cal 1 that you know the antiderivative of.
Secant squared?
Secant squared x? Okay. So if we look at the function f of x equals secant squared x, Omar, what is the general antiderivative of that function? Tangent x plus c. All right, so that's, again, going off of what we know about Cal 1, we know the derivative of tangent x, right, is secant squared x. So the antiderivative of secant squared x is tangent x plus some constant that gives you the whole family, right? All right, who wants to volunteer another one that you know from Cal 1? You can only volunteer once. I have the sticks too. Charles. Where's Charles? Did I bring him? Charles? Okay. Charles, can you think of anything from Cal 1? Trig? Any trig stuff? You know, derivatives? What's that? Cosecant? So do you know the derivative or anti? Okay, how about sine of x? Derivative of sine of x. What is that? cosine of x, right? So if I start here with cosine of x, then I know that that came from taking the derivative of sine of x, right? So you take derivative of this, you get that. So if I slap a plus c on here, there's the whole family of antiderivatives for cosine. Who wants the next one?
Sine of x.
Sine of x. So this one we have to be a little careful with, right? So you want me to put sine x here? Okay, so what would you have to take the derivative of to get that? Negative cosine x. So look, this is our first kind of like, be careful. Because the derivative of cosine of x is negative sine x, right? So if I start with sine x, you need, so that when you take the derivative of this, you get positive sine x. So that by itself, derivative of that would give you negative sine. That's not what you want, so you just slap a negative in front. All right? Recap. Antiderivative of secant squared x is tangent x plus c. Antiderivative of cosine of x is sine x plus c. Antiderivative of sine x is negative cosine of x plus c. Any others? E to the x. Yeah, e to the x. And what's the antiderivative? E to the x plus c. That's a nice one. It's hard to mess e to the x up, right? Because no matter which way you go with it, it's the same thing, right? Okay.
1 over x.
1 over x, good. So 1 over x, that was a special one. We kind of learned that kind of late in the, where did it come from? Natural log, the natural log of x. The natural log of x. And then we do plus c. Okay? So do you all agree with that? Natural log of x? I take derivative of natural log of x, you get 1 over x. So the antiderivative of 1 over x is natural log of x plus c. Now, if you look at your formula sheets, you're going to see this absolute value around the x. And the reason we do that is because natural log is not defined for negative numbers, right? It is not. But is this defined for negative numbers? Yes?
Yes.
It is, right? You can plug negative numbers in here, but you can't in here. Can you plug 0 into this? No. Can you plug 0 into this? No, you cannot. So what we've done by putting absolute values, we've said, look, the only problem you're ever going to have over here is when you have 0, but that's okay because 0 doesn't even go into this. But now what you've done with the absolute values, you've found a way to define the antiderivative where it's valid for every value of x that goes into this also, positives and negatives. All right, we need to move on to another table over here, run out of room. Anyone else have something from Cal 1 they remember? What's that?
Negative sign.
Negative sign. So what if we change this to negative sign? Then this would change to what? Positive cosine. So I'm going to include that in this line. It's like that's covered.
1 over the square root of 1 minus x squared.
Oh, wow. Okay. So 1 over square root of 1 minus x squared. Okay, where did that, what would the capital F of x of that be? Arc sine. That's what we talked about last class. But see, that's now fair game. All right? We learned last class that if you take the derivative of arc sine of x plus c, I'm going to be off the camera, but, right? So the derivative of arc sine of x plus any constant should give you that. There was one from last class that I put a star by, didn't I? Which one was that one? It was the arctan one. So 1 over 1 plus x squared. And that means the antiderivative of that would be arctangent of x plus c. You see how this works? And we could keep going. I mean, like anything that we learn the derivative of in Cal 1 in terms of like the nice things. I mean, of course, we're not doing any product rule or quotient rule here, but just the straight derivatives that we learned in Cal 1. All of those going backwards, we should be able to go backwards. I'll put one more up here just for you. Maybe two more. I'm gonna put that one up there because I really want everyone to remember this and know it and just be like almost like breathing to you. What do I have to take derivative of to get 1 over 2 root x?
The 1/2 square root of x.
The square root of x plus c. Or if you want, you could say x to the 1/2. But the derivative of the square root of x plus any number is 1 over 2 root x. Maybe I'll come over here. How about this one? Negative cosecant x cotangent x. Now, honestly, I wouldn't expect you, like everyone, to remember that one. But there, on your formula sheets from Cal 1, you should have this derivative on there. Cosecant x plus a constant. So the derivative of cosecant x is negative cosecant x cotangent x, right? So it's just everything we learned kind of backwards, right? We just have to know that. Okay, so let me try something else up here that looks somewhat simple. What about this? Herman. So Herman.
Secant squared x plus c.
Okay, so let me put it up here, and I want you to think about that. Is the derivative of this this? Or is it the other way around? It's the other way around, right? When secant squared x is here, then the tangent x would go here. But if I put tangent x here, then you're asking yourself, where in Cal 1 did we ever take the derivative of something and get tangent x? And it never happened. We actually never had that happen. Okay? So we don't have an easy way. This was a trick question. I apologize, Herman. Okay? We don't actually know that right now, do we? Now, there's a formula sheet, and you could look it up, but that's not the point. The point is, right now, what we know from Cal 1, we don't have a way to go back, do we? From tangent? You all agree? Well, let's see. We could go back from sine, right? Sine, we went back. Cosine, we went back. But tangent, we can't. We can go back from secant squared. We can go back from negative cosecant cotangent, right? But tangent didn't work. How about some of the other trig functions, like cotangent? Did we ever take the derivative of something to get just cotangent? How about secant? Just secant by itself. Not secant squared, but just secant. Derivative of something to get secant? Oh. So what's my point here? Still stuff we don't know, right? There's still open questions here. We will find these antiderivatives. We will. All right? We're just not ready for them yet. Okay, so the end of the, not the end of the section, but the next major point of this section is that, look, you have a bunch of things from Cal 1 that you should know, including stuff with inverse trig functions. The book has a summary, like a table, where it summarizes a lot of the things that you should know, okay? Don't go memorizing. I'm not trying to get you to memorize it, but the book is saying, hey, look, these are the things you should know already. Now, there's one more thing that we have to look at before we move on to the next section in terms of finding antiderivatives, and that is, you know, what if we had something like, I don't know, x to the 4th power, and we wanted to try and find its antiderivative, the general form. Well, would we all agree that whatever function we put here, when we take its derivative, we have to get x to the 4th?
Yes.
Which means that if I look at this as being x to a power, what would the power have to be in order to end up with x to the 4th? 5, because remember when we take derivatives, you subtract 1 from the power, right? So we already know that much, but that doesn't work. Why doesn't that work?
Because the 5 would be in the
Yeah, because the 5 would come out, and we don't want the 5 there. We want a 1 in front. Yes?
X to the 5 over 5?
Yeah, so we could just basically scale this by 5. You said just put it over 5, and that would work, wouldn't it? And then we could say plus c, and then now we'd be in business. Now, another way we can write that in the way that I will write it, you'll see me writing it all the time like this, is this. It's the same exact expression, right? It's the same exact expression. And we could do that for pretty much anything, right? Any power of x we could do this for. How about x to the 82nd power? Well, we would want the power on that to be x to the 83rd power, right? But we wouldn't want that 83 to come down and be in front, so we would have to put a 1 over 83 out front, and then we'd add a constant to it. And that would work for almost every power of x. There's one power it wouldn't work for. How about this? Now I'm kind of disguising this. What is this really? This is really 1 over x. This is really 1 over x. Didn't we already do that? What was the antiderivative of 1 over x? It was natural log of x. But let's try and use this same idea that we were using here. What would we know the power would have to be? We'd have to add 1 to this power, right? So -1 plus 1, you get 0 here. But then you want 1 over... Yeah, that's not going to work. But it's okay, because we know what to do with that case, don't we? With that case, it's natural log. So let's see. We're going to come up now with a general formula. If we change that power up there to n, then if we want to find the antiderivative, what we will do is put x to what power? Whatever that is, add 1 to it. But when that n plus 1 comes down with the derivative, we don't want it there, right? So out front, we put 1 over n plus 1 out in front. So that's like the 83, and that's like the 1 over 83. And then we say plus c. Y'all see that? Now, in your formula sheet, I believe they write it this way. It's the same thing. The reason I like this form better is because, like, if you have to take the derivative of something several times, I just like the constants to always be out front. So it's just easier to work with them if they're out front. That should work. And I think if you look at this formula, you can see now from the formulas that there is a special case when n is a certain number that this formula will break down. And you can see it right here. If n is -1, you've got division by 0. But we know what happens when n is -1. The antiderivative is natural log absolute value of x plus c. So these two together, this along with this, covers all powers of x. Every power of x that covers. And so we call this the power rule for antiderivatives. Not to be confused with the power rule from Cal 1. The power rule from Cal 1 was this one. The derivative of x to the n is n times x to the n minus 1. That was your power rule from Cal 1. Take the derivative of x to a power, you bring the power down, you subtract 1 from the power. We're going backwards now, so it's still a rule that has to do with powers, but we use it when we're doing antiderivatives. You add 1 to the power and you scale by 1 over that power. All right, let's see if we can use this rule to do a couple of examples. That rule is in your formula sheets, but I'll write it down over here off camera. If that, then the antiderivative (1 over n plus 1 x to the n plus 1 plus c). All right, so let's try one. So as an example, let's say f of x is equal to 3x to the third. Find capital F of x. Find the general antiderivative, and I'm going to call on somebody. Alberto. Where's Alberto? Alberto. Okay, take your time. While you're doing it, Alberto, I put a 3 in front. I did that because we haven't talked about that. Okay, so what do you think happens to the 3 that's in front? Let me ask it this way. If I were to ask you to take the derivative of this, back in Cal 1, if I asked you to take the derivative of this, what would you do with this 3?
I mean, I would bring the exponent.
Down, multiply it, and that'd be 9, right? So the 3 just kind of came for the ride. Nothing happens to it, just comes with you. Do you all agree with that? But when you do antiderivatives, the exact thing happens still. So what I want you to do, Alberto, is just kind of ignore the 3, okay? Just bring it with you, and then really just focus all of your attention on trying to find the antiderivative of that, okay? So use the rule. What's the power on x going to be? 4. So I'm going to leave a little space in here, x to the 4th. And then what needs to come out front, Alberto?
The 1 over 4.
1 over 4. So 1/4 out in front, like that. Do y'all see that? So the 3 just comes for the ride, and then we just take the power rule on that, and then I need plus c. And I should probably not leave this like this, right? I just make that like 3/4. X to the 4th plus c. Yeah? Now, the good news with Cal 2 in antiderivatives is that you can always check your work, right? You can always check your answer. All you have to do is take the derivative. And if you take derivative of this, you better get back the original problem. So does it work? 4 comes out. Yeah. You could look at it like 4 hits the 3 becomes 12. 12 over 4 is 3. Or you can say the 4 comes out, cancels, you're left with the 3. However you look at it, you're still left with 3x cubed, right? Okay, let's do another one. And who's up here? Deborah. Deb. Okay, Deb. Deb. You want me to go Deb? I'll go with Deb. That's my sister's name. Okay, Deb. So how about this? It's not intended to trick you. It's just I want to see what you do. Just think of it from a Cal 1 perspective. What would you take the derivative of to get that? Well, I agree. The derivative of that would be 0. But I'm asking, what would you take the derivative of to get that? X? That's all I heard. Is that what you said? Or did you say something else? I didn't hear. What's the derivative of x? 1, right? So if I take derivative of that, I don't get 8, so I'm missing something here. 8x, right? 8x plus c. It's a lot different when I call on you, right? Pressure's a little different. 8x plus c, that you agree? Now, that we did just by thinking about Cal 1. But does the power rule work on this one? It does? Who said yes? How does it work? Can you explain how that actually works?
It says if there's a x to the power of 0.
Yeah, see, you have to look at this right here next to this as being 8 times 1, which is really 8 times x to the 0, because x to the 0 is 1. And now if we do that, we should have 8 should come for the ride, and then we're going to take x, we're going to add 1 to the power. What happens when we add 1 to 0? We get 1, and then out front we're going to do 1 over what? 1. And that's just 8x, isn't it? So the power rule actually does work there. We just don't need it, because we know from Cal 1 that take derivative of 8x, you're just going to get 8. And wouldn't this work for any constant? Like if this function was the function -4, the antiderivative would be -4x plus c, right? So for any constant going backwards, you're just going to tack an x onto it. All right, let's do another one. How about 4 5th roots of x squared. Find the antiderivative of this. Let's see who the lucky one is here. Shay? Yeah, write it down. Then I want you to kind of just talk through it more than I want you to like work it out and give me an answer. So help me kind of work through what your thinking is on this.
So I have to rewrite these ones. So I wrote
Okay.
it as 4x to the
Okay, so good. You first have to realize that when you have a